Thank you very much for this very nice introduction. Good morning, evening, everyone. I will report on a joint work with Roser Homs Pons, Joachim, Jelisiejew, and Team Seynnaeve. The work is on archive, and I will start by presenting some motivations to construct tensors using algebra and algebraic geometry. About tensors in a triple tensor product. So three-way tensors, three-order tensors, W1, tensor W2, W3, W1, W2, W3 are just vector spaces. And given a tensor, I would like to talk about it and present it in different ways. So one way is that I can say that a tensor is just up from a product of two vector spaces to the third vector space. And if you would like a different notation for such a two-linear map, namely using the usual, I would say, mathematical notation for a tensor, if you're given a map F, the tensor in the triple tensor product is just given by this formula below. So you have to look where the basis vectors, pairs of basis vectors, are mapped to through F, and like that you obtain a representation of your tensor. Just to say that the tensor is a linear map from a double tensor product to a vector space. Okay, so above I have two linear maps from a Cartesian product, below I have linear map from the tensor product. And if you accept this, well, you can also look at the dual of it. And if you have a double tensor product, you can identify it just with a space of matrices of homomorphism or homomorphisms, just linear morphisms. And like that, we can say that the tensor is just a map from a vector space to the space of morphisms, so a linear space of matrices. And here we can see a few different points of view of, and I believe that different people may prefer different points of views. It would be great if you're familiar with at least one, and if you're willing to accept that the other ways are completely equivalent. So linear spaces of matrices, two linear maps, or the usual notation where we use tensor product of vectors. Okay, and I will like to use a few of those interpretations because some of them are easier to introduce a tensor, some of them are easier to present it. Now, if we take this point of view, the operation of multiplication is obviously a tensor. Why? Because it's a two-linear map. Matrix and another n by n matrix, we can multiply them, obtaining an n by n matrix. So here mat n is the vector space of n matrices, and matrix multiplication is a two-linear map, hence a tensor. It's just a point in the tensor product of two, but that's not so important. If you would like to see the same tensor interpreted as tensor products of vectors, well, there is a natural basis for n by n matrix. J is just a matrix that has one on the entry ij and zero otherwise. And the tensor becomes then just a sum over all possible ij and k, where we take a basis vector eij, we tensor it with a basis vector ejk, and we tensor this with the basis vector eik. So whether I put the indices up or down, I only distinguish it to make a distinction between a dual space or the primary space. You all of the indices down. And what I would like to stress here is that this presentation, if you are a computer scientist, you can also read it as an algorithm. An algorithm two n by n matrices. Namely, this algorithm tells you that you need to sum all of the ways where you take the ijth entry of the first matrix, multiply it by the jkth entry of the second matrix, and put it in the ikth entry of the result matrix. Okay, so I would also like to present matrix multiplication as a space of matrices. Well, it has to be a space of n square by n square matrices, because our vector space has dimension n square, and I will do it as follows. First, n by n matrix just filled with arbitrary entries. So all of them are completely arbitrary. This is an n square dimensional space of n by n matrices. And it turns out that as a space of matrices, this matrix multiplication tensor simply has the block form as follows, where on the diagonal, I put this n square dimensional space of matrices. I repeat it in blocks, and all the other blocks are 0. So the low square by n square space of matrices, it's divided into n by n blocks, each one of size n by n, and the blocks on the diagonal have all distinct entries, but as you go along the diagonal, the pattern repeats. Okay, so these are different ways to view the matrix multiplication tensor. This, you obviously see that the rank of this tensor is at most n to the third. So this is this canonical polyadic decomposition, or simply like the rank presentation. But what is surprising is actually not the rank presentation, because you can do better. The first example is due to Strassen, also known as the Strassens algorithm, who observed that even when you take n equal to 2, the rank is not 8, but 7. Okay, so I think what is surprising here is that you can actually present a tensor as a sum of 7 simple tensors. I would like to stress that you can, why do I call it Strassens algorithm? Because you can read the right-hand side as an algorithm. Well, very precisely, I'm starting to read it. It says, take a 2-1 entry of the first matrix and add to it the 2-2 entry of the first matrix, multiply it by a 1-1 entry of the second matrix, and put the result into a 2-1 entry of the result matrix and the 2-2 entry of the result matrix. Add to it, and so on and so on. You have to do 7 such quite complicated things, but it's a completely different algorithm how to multiply 2 by 2 matrices than the usual one we all know. Now, I would like to say, why are we so much interested, and why was it so interesting in the case of 2 by 2 matrices? You probably would just multiply 2 by 2 matrices using the usual algorithm. Well, it turns out that there is an operation on tensors that is a product. And I would like just to present an interpretation of this formula, that if you take matrix multiplication for A by A matrices and B by B matrices, if you do this product operation on the tensors, you get matrix multiplication on matrices of size A times B. Well, what does it say in practice when we think about it as an algorithm? It tells us that if we have an A times B matrix, so let's say a 4, we could as well treat it as an A by A matrix with entries that are B by B matrices. So if you have a good algorithm to multiply A by A matrices, you can also use it to multiply A times B times A times B matrices. Okay, so you can look at your Foibar array 4 matrix as a 2 by 2 matrix with entries that are 2 by 2 matrices, and you can apply Strassens algorithm for that. And of course, this goes up. Now, when you can apply 4 by 4 matrices, you go to 8 by 8, 16 by 16, and asymptotically, you actually get a gain. This is a faster algorithm than the usual one to multiply matrices. Well, and if there is a faster algorithm, you can ask, what is the possibly fastest possible one, which allows us to introduce the constant small omega. And small omega is the infimum such that the complexity of matrix multiplication is O of n to tau. So more or less, a lot of people will say that matrix multiplication is of complexity O of n to omega. This is not correct, but it's almost correct. So you can think that basically this n to omega is the complexity of multiplying n by n matrices. Now, this is the complexity point of view, but there are points of view purely algebraic. It turns out that you can forget about algorithms and just focus on the rank of your tensor Mn or on the border rank of your, and hence, if you know any of those for n large enough, you basically determine omega, small omega. Okay, I will not repeat the definition of a rank and border rank unless there are questions. I know this was present in the previous talks. So what happens now? Well, as said, we want to determine omega, and there has been a lot of progress on this. We know it's strictly smaller than 3, and I would say that for last maybe 30 years, the methods are as follows. You do not directly bound the rank or border rank of the matrix multiplication tensor. Instead, you look at a different tensor. Here is an example of a different tensor known as the Coppersmith-Winograd tensor, and I present it as a space of k plus 2 times k plus 2 matrices, as a k plus 2 dimensional linear space of k plus 2 times k plus 2 matrices. Well, what do you have to do with this tensor? First, you have to divide it into pieces, and here I made the division for you. You have to understand each piece and see that, in fact, it's some kind of matrix multiplication, and you need to have a border rank of that tensor. Once you know all this, there is a machine developed by Coppersmith and Winograd and enhanced by many, many people, that from this information cooks up a bound on omega. So from the tensor above and the blocking as above, this machine will tell you that omega is less than 2.38. And what I would say is astonishing is that, well, I said that for over a quarter of a century, people have been working very hard on this, getting new bounds and so on. But almost all of those results, they are based on exactly this Coppersmith-Winograd tensor, which was just given to you by Coppersmith-Winograd, not really maybe motivating why. I mean, they don't have to motivate, they just give it to you and they tell you, well, it gives a very, very good bound. Now, as you can see, there is a conjecture that omega is actually equal to 2. Clearly, you cannot go beyond 2 because you cannot multiply n by n matrices faster than n squared, because that's the time to output. It's also easy to see that the rank cannot be so small. But I would say that this is a very striking conjecture because it says that in some sense, for very, very large matrices, multiplying them is not so hard. It's in fact not much harder maybe than adding them. And because you add them in time, basically O of n squared, well, there is this infimum here, but still people believe or expect, hard to say, that maybe multiplication is not so much harder. Okay. Now, I would say that this is a very successful story, that quite a lot of deep mathematics allowed to prove existence of first algorithms. So on this slide, I would like to counterpart it with some bad news. Namely, it turns out that this tensor, and as I said, almost everyone for the last 30 years is using this tensor, should not allow you to prove that omega is smaller than 2.3. And even if you allow more general tensors, which I will describe in a second, that so-called come from smoothable algebras, they should not allow you to prove the main conjecture. And all these results in various forms, they were presented by many different people. I'm here stating them quite informally. So of course, these statements are formal, but the message they convey is equivalent to the one on the slide. So what can we do when we see such bad news if we would like to prove a conjecture? Well, either we need new good tensors and maybe even families of tensors somehow. So maybe we should not apply this Coppersmith machine tensor, but have a good family of tensors to which we could apply it and get better bounds. Now, tensors are everywhere, and as we know, all of us encounter various tensors every day, and they are distinct. So how to detect a good tensor? Unfortunately, this is quite hard to say what will be the bound on omega from a given tensor before you actually make this whole Coppersmith-Winograd machinery run. So if you give me a tensor and you don't tell me much about it, it will be very, very hard for me to say what's the bound on omega from this tensor. So how to look for good tensors? Well, we could try to start looking around the Coppersmith-Winograd tensor. That is, we could try to start exploiting the properties of the Coppersmith-Winograd tensor and see if there are other tensors with such properties. And here comes two properties that I don't expect are understandable at this point, but I would like just to say them and then go into details. Namely, Coppersmith-Winograd tensor comes from a smoothable local algebra and is a highest weight vector. Okay, so after this introduction, I would like to say a few words how to use algebra and these two somehow families of tensors to construct something that could potentially work to bound. Okay, so the first thing I would look at will be n by n matrices. This is a vector space, which I denote by mat n. And on this vector space, I can look at degree 3 homogeneous polynomials. So degree 3 homogeneous polynomials on n by n matrices also form a vector space, a much bigger vector space that I denote by S3 of mat n. Okay, it's a vector space of homogeneous degree 3 polynomials on the space of n by n matrices. Now, what do I mean that this space decomposes? Well, I can look how the group GLN of invertible matrices acts on this space. So GLN acts on n by n matrices, so it also acts on polynomials on the space of n by n matrices. And I can call this vector space a representation. And this representation is in fact a finite sum of irreducible representations that do not break into further pieces. Okay, so I look at cubics on n by n matrices and I decompose it. This was done when Tim was still my PhD student. He obtained a complete decomposition. Yeah, so I have a big vector space and I write it as canonically as a sum of smaller vector spaces. Now, each of these smaller vector spaces contains a special God-given vector known as the highest weight vector. Okay, no choices, something very natural. You don't have to fix a basis or anything like that. And I believe that it's very natural to ask what are those highest weight vectors on this space. And we were amazed because it more or less turned out that half of them were Coppersmith-Winograd tensors. Sizes depending on n and so on. But if you didn't know Coppersmith-Winograd tensor, if you were just interested in the space of cubic, you would find Coppersmith-Winograd tensor coming to you naturally without having to look for them in the literature or some combinatorial construction. What is maybe interesting is that not all of those highest weight vectors are Coppersmith-Winograd vectors. So at least from my perspective, it's very natural to say that these other tensors are also very good candidates to bound omega from above. So we analyzed one of them. It turns out it has minimal possible border rank. Well, and the Coppersmith-Winograd tensor, but it was 2.45, which I think is considered not bad. I would also like to mention that the symmetrized matrix multiplication is also one of highest weight vectors. This symmetrized version of matrix multiplication also appeared in many other works. And if you can estimate the rank or border rank of that, you would also win and get the optimal bound on omega. And we conjecture that basically all of those highest weight vectors have not too big border rank. Okay, so this is one family. If you're interested how the tensor we analyzed look like, here it comes. So this is a space it's a 3m plus 5 dimensional linear space of 3m plus 5 times 3m plus 5 matrices. And if you've been studying matrix multiplication before, you will see that it has a structure into blockings where the blocks, they look very much like matrix multiplication tensors. There are these blocks of distinct letters and they repeat. So for this reason, it's quite good to run the Coppersmith-Winograd machinery on it. Okay. To construct interesting tensors from algebra. Now, it turns out that if you consider the word algebra literally, which for me means a polynomial ring modulo an ideal, so a polynomial ring is in particular a vector space. If you assume that this vector space is finite dimensional, you call the algebra finite, you can really construct from an algebra a tensor. Why? Well, because multiplication in algebra is a two-linear map. Yeah, if you take one element from A and another one, and if you return their product, this is a two-linear map. Hence, there is always an associated tensor, TA. Every algebra gives you a tensor. Now, I wanted to present here one theorem that this tensor TA is symmetric if and only if A is Gorenstein. This is from a joint work with Amy Huang and Emanuele Ventura. Okay, so we have a lot of tensors, and by the work of Blazer, Lisikov, and Landsberg, it turns out that in many cases, we can say that they are of minimal border rank, that is the dimension of the vector space, and the condition is that the algebra is smoothable. This is a condition very well investigated in algebraic geometry. Okay, so how to construct interesting algebras? Well, I would like to give you one method to do that. If you take any set in a polynomial ring, you can look at all derivatives that annihilate that set. And this is an ideal. And if you quotient out the polynomial ring in the derivatives by that ideal, you always obtain a finite dimensional vector space. I will here assume that S is finite, and AS, it turns out that this quotient ring is Gorenstein. This interesting property I have already mentioned is that if you start with just one polynomial, yeah, so you pick a polynomial and you look at all derivatives that annihilate it. Let me give you one example.
Yeah, Mateusz, sorry, here, just for the interruption, just a short reminder that you have about 5 more minutes.
Perfect, thank you. So I pick x1, x4 plus x2, x3. I look at derivatives that annihilate it. So for example, if I derivate twice with respect to x1, I get 0. So I put there this y1 square. Then I put y2 square, because if I derivate twice with respect to x2, I also get 0. And then I obtain the whole ideal of derivatives that annihilate S. And if you look at the quotient ring, well, it's a finite dimensional space that has a basis, element 1, y1, y2, y3, y4, and the product, y1, y4. And if you look how you multiply in this basis, you get a tensor, the structure tensor of the algebra, and you should already recognize it. Yeah, this is the Coppersmith-Winograd tensor. So that's another way the Coppersmith-Winograd tensor naturally comes to you. It's just an annihilator of a quadric. Okay, the associated to the algebra that comes from the annihilator of the quadric. So this one is smoothable. That's why Coppersmith-Winograd is of minimal border rank. But it turns out that there are more general theorems in algebraic geometry due to Cartwright, Ehrman, Velasco, and Virey. Namely, you can take any two quadrics, and then this annihilating set will always define a smoothable scheme. Okay, so it means that for the Coppersmith-Winograd tensor, instead of using just one letter in this big block in the middle, we are allowed to use two letters, and it will be still always of minimal border rank. So the best one we could come up with, so the only requirement is that this middle block, it needs to be symmetric, but the gain is that you can now put two letters as you wish, not one letter, but two letters. This is the best one we could come up with, which led to omega smaller than 2.431. Again, I'm not sure if our analysis is optimal. Quite the contrary, I believe it is not, but I believe it's a very nice source, the smoothable local algebras of minimal border rank tensors that are potentially good to bound omega from above. So you could ask why algebras, because there was this negative result that the smoothable algebra will never allow to prove that omega is equal to 2. Well, but it's quite easy to prove also the opposite theorem, that it's enough to look at local smoothable algebras to get as good approximation of omega as you want. So for any epsilon, there exists a local smoothable algebra A of length L that degenerates to matrix multiplication and basically proves that omega is smaller than the best possible bound plus epsilon. So restricting to smoothable algebras is not a loss. I mean, you can just do local smoothable algebras and not be doomed to fail to estimate omega. So what kind of algebras do we suggest? Well, first of all, graded algebras. Yeah? So polynomials come with a natural grading. They are very good to run this machinery of Coppersmith because they basically provide you with the blocking. If you know what the element has a degree, then you can merely make a blocking according to that degree. Now, the last point that I would like to make is that monomial algebras. So you can take any ideal which is generated by monomials, then it's quite easy to prove that this is always smoothable. And this will always give you a graded algebra. And there are really many monomial algebras. Every single one will give you a bound on omega. But I don't think they were really investigated a lot in the literature, maybe because there are too many of them. And those that are very easy, they don't give grade bounds. But I think this could be one of the possible ways to investigate and look into. Thank you very much.